Hello, my name is John Olson, and this is my analysis of some applications of first-order differential equations to the real world. Within this document, the author explored multiple types of equations shown throughout everyday life. The one that I'll be focusing on is Newton's law of cooling. The equation shown below, and there's also variants of the equation like the second one shown below that. Newton's law of cooling can be used and perfected to help engineers run simulations and understand how quickly items can be cooled. The difference between the two equations is how you find the k value. In the left equation, you can see that an exponential is used according to time, and the right equation is a simplified equation where the k value is 0.5. In the right equation, we are using dt over dt to represent the change in temperature with respect to time. As I said before, 0.5 will be the k value in the right equation. T will be used as the temperature and also represent the initial temperature, and the 60 will be used to represent the outside temperature or the temperature that we are using to cool the object. Here is my Simulink design. It is also very important to note that my k value is a negative, meaning that heat will be taken away instead of added. While looking at the design, my initial value setup was 120 degrees and the outside temperature was 60. If we assume that the K is negative 0.05, we are assuming that the outside temperature or the ambient temperature will not change due to the fact that there is so much more. I use an example right here on this slide where I talk about a piece of metal dropping to a pool. The pool water probably would not change temperature. Here are the results. It took 100 seconds to go from 120 degrees down to 60 and to be even with the water temperature. I changed up the temperatures a little bit. I gave T not 200 degrees and I gave the T atmosphere 80 degrees and I kept the K value the same. You can see that the graph kind of simulates the same slope and the time was also similar. After this, I changed up the K value. I changed it from negative 0.05 to negative 0.0005. And I left the temperatures the same as the last one at 200 for the knot, and then the temperature of the atmosphere being 80. And you can see how much it affected it. Our time to cool went from 100 seconds to 10,000 seconds. I learned that if you really want to adjust the Newton's law of cooling equation, you need to really affect the K value. The differences in temperature aren't too significant, but the K value is what's really significant. We can use this in applications where we design engines, machines, or anything that needs cooling. And here is the article that I used all this information from.